It's a pleasure for me to be here and have the possibility to tell you a bit about my project and take you with me on this little journey. The topic today is also digital transformation. It's a bit linked to what Sebastian told before. We are also talking a lot of digital twins in our company. And especially I want to focus on the part of testing, verification, validation of the products. And here I want to take you with me on the journey of moving from physical testing to simulation. So the end of the journey will be that you saw that how we reduced actually the effort for a testing campaign from 4 weeks down to 1 night. So that's a bit the main goal that you see this. Besides this, so there are 2 key takeaways I want to give you. One is digital transformation is actually a change management process. People are always talking about tools, they're talking about data and so on, but in the end, digital transformation tackles organizational structures, processes, tools, implementations itself, and this is really the real challenge is the change management in. And the other thing we also heard this day already, so model-based approaches are driving fact-based development, and this is also something we're really looking forward in our company. Yeah, so that's a little bit the roadmap. I will quickly tell you something about Schindler, who we are, what we are doing, and then I will tell you something about my project. It's called Eden, and about the 2 examples of the deployment or of the execution applying of these things. So Schindler was founded in 1874 in Switzerland. It's a real Swiss company. We are focusing mainly in vertical and horizontal transportation market. And our products are elevators, escalators, so you most probably know our product and used it several times, even if it is not that spectacular in the first round. So as Andrew already told, so it seems a bit like they're just going up and down, opening doors, and that's it. But it is a bit more. And we are located in all kind of urban areas, commercial, residential buildings, airports, train stations, as well as big ships. And our products are moving today more than 1 billion people. So goals and challenges of digital transformation, especially in our industry, or maybe just in our company, but I think also in our industry, physical testing is very, very present. That's a bit related also to we're originally a mechanical company. Software is becoming also very, very important. We have a late integration of mechanical, electrical software stuff and so on. So therefore we invest a lot of time and money in integration tests late in the process. So just 2016, we spent around 3,200 hours just for software testing. So just for the release tests for our software. And overall, I think per year, we are just spending around 2.3 million Swiss francs for physical testing in our real installations and test towers. And we want to get rid of a bit of this, not of all, but just a bit of this. The other thing is that we have a high complexity regarding variance in our system. I think it's a bit here. So just having a high level look on different system architectures we're having. So then it comes out that there are 20,000 different system variants, and every of these variants contains different component variants again. So we will come up with a variety of the product which is huge and which is simply exploding, and we are simply not able to test every of the possible variants. So an elevator, if you buy an elevator, most probably no one else in the world has this one you buy from us. So it's very, very customer specific. So and therefore it's so hard to test everything. So Eden, so how we try to tackle all these things. We have this nice project, or today it's more product. It's called Eden, the Elevator Dynamics Environment. And it was started as a pilot project, focusing mainly on the mechanical, physical behavior of the elevator system. As I mentioned, we have a huge variety. Also regarding mechanical stuff inside the elevator. And therefore, this was the main focus in the beginning. But very, very fast, it turns out that you cannot make use out of this mechanical model without any software model, without any electrical model, because you just have to run these things. And in the end, now today we have more or less a digital twin on the mathematical side of our elevator system. And today it is a whole modeling and simulation framework covering processes, covering different applications for system-centric validation, system-centric analysis, for an holistic development process for our elevator products. The product itself or the project itself is globally established, so we're working together with colleagues from North America, from China. The development is taking place in India and in Switzerland, which is what is really cool. Maybe a bit regarding the timeline. So we were starting this project roughly 2 years ago in July 2017. Today they're working more or less 4.5 people on this. It's an agile project. I think that's the only thing how you can manage this, because it was more bottom-up driven than top-down. So the requirements for all these things were not that clear, and day by day there are more customers requesting new features in the model and so on. So this is the only way to handle this. And also, of course, we're participating. We were having a huge benefit from the collaboration with MathWorks regarding training, also consulting, their technical support, and so on. I brought 2 models with me. So on the left side, so on the left side, that's an elevator. And here on the right side, that's also an elevator. So as usual, there are 2 models, so both of them are wrong. So the question is a bit what kind of question you want to answer with which model. So you see here, it's the graphical representation of this. So most of you will recognize maybe this part. So it's the landing door in the upper floor and the inside of the cabin. And I just want to give you a quick introduction on how an elevator looks like. So we have the mechanical part of the elevator, so what you're mostly knowing, as I mentioned, so the cabin, counterweight, the whole roping system. Then we have the so-called traction sheath. So this is to transfer the power of the motor via friction into the mechanical system to make the whole thing move. We have the whole power electronics part with the motor, the machine brake, the safety system, sensoring system, the whole software part, the user interface, so the buttons you're pressing, and the power supply. So in the end, we covered everything of our elevator in this model. And here are some little interesting facts maybe. So there are around 11,000 blocks now in this model. It's a generic system model, so every of these 20,000 different variants are covered within 60 architectures in this one model, which is parameterizable with roughly 350 parameters. And due to the fact that we are using Simscape for the modeling of the mechanical and electrical parts, so we are covering today more than 1,500 physical signals inside this model. So then I quickly will tell something about how this is all working regarding the development process with MATLAB and Simulink. So we're having our development environment. We are talking also about deployment, even if Matthias said that deployment is not his favorite wording for this. So it's more the application of what we're doing, and then how the project management is connected. So you see here, so we're using for the data management, the whole MATLAB project stuff. There's a huge layer of automation, scripting, data dictionaries, GUIs with the app designer. Also the documentation is done inside the models and transferred automatically to HTML files, which are automatically hosted in our own documentation system. So there's a huge process automation chain behind this also. The modeling, as I mentioned, is taking place in Simulink and Simscape. And then what else? What is also really, really important is the part of model in the loop testing. So verification of our models. Because, so as I mentioned, 11,000 blocks, whenever you change something, it is not predictable whether you also changed something else you don't want to have. So therefore, this is really, really important. We're covering this today with Simulink tests. The deployment environment here, it's about code generation again, and then how to bring it to the customer. So there are two things I will talk about. So it's more the app-based web deployment with the MATLAB web apps, and it is about hardware in the loop deployment. So hardware in the loop, quickly, for those who do not know what this is, it's in the end the method to test the system under test and to connect it to a model to extend the context of where the system under test can be tested. In our case, we are just bringing the mechanical system as a model to our software controller and test it together with the mechanical system, even if the mechanical system is not there. So we're just faking it with the model. For the project management environment, just to have it complete, so as we are working agile, we are using Jira, Bitbucket, Git, Jenkins for the process and automation. Everything is really integrated in one big process using REST API via MATLAB for communication and so on. So it's really well implemented. That's quickly process workflow. So as I mentioned, it's well established all over the world, America, India, Asia Pacific, ABCon, so where we are located. So we're getting field issues, development task requests, model requirements from experts, application requirements, application requests. We're just taking all these things and then in a normal agile project process, we're just covering the things and implement it. With the process automation, after the implementation, we're triggering directly the model verification. So the model in the loop tests, what is done in India. We also have the possibility to directly ask for measurement data. So giving measurement requests to the different sites using their installations there to analyze and validate what we implemented. So one of our applications, the Garden of Eden. So it's a bit, sounds a bit pathetic, but in the end, it's our own web app server. It's a bit like if you're going in your iPhone to the App Store, so you will find a bunch of applications there. And here it is the same, not that much. So today we are covering 8 applications, but it's still okay. And the goal was really to enable the people who are not that familiar with Simulink, MATLAB, to use what we have done. And even if you are familiar with MATLAB Simulink, it will cost you huge amount of time to go through it and to understand what happens with all these 11,000 blocks. So therefore we said, okay, maybe we must change this and to enable the people in a different way. And therefore the MATLAB web apps was really perfect. So we built graphical user interfaces to spot on really specific points in the model, because every application in the end is connected to the same model. So it is this one model we showed you, but the graphical user interface is just pointing on one specific application. So for example, there is a specific test case called pulsed evacuation brake opening. So it's a safety feature if you're stuck in the elevator. And just to get there to activate it in the model, it takes a bit of so you have to activate some states inside the elevator, and just to come over this, we prepared a specific graphical user interface for this to spot on this specific part. And the web apps, it's really cool. So you do not need any license for the users, so they can just enter it via the internet, via any internet browser. And this is working really cool. So I now try to show you a little video. So this is our web apps. You see the configuration interface here. I talked about 350 parameters. So this is guiding the user to have an idea what kind of data he has to input. Here we are changing the machine brake of the elevator machine. You can create a bunch of different configurations. In the end, you gather a real configuration set. This has roughly no limit. Normally, you get so inside one application range, we are covering 60, 70, 80 different configurations. And with this, you can configure all the things. This is also linked to local parameter databases. So for example, you saw that there's a huge list of machines. So we have roughly 1,000 different variants of machine types. So, and all the parameters are directly linked there in a database. You can export it then, so it's exported as a MAT file. You can also export it as an Excel file, download it, have it locally on your PC. Then you go into the elevator system simulation app. This is more generic app to just handle the elevator. Import the configuration file. So now I can see if you have a look at the brake there, 195. So this, yeah, now we see it here. So the second brake was changed. So the graph changed a bit. So now this was loaded, and now we can simulate the elevator. So there's a little graphical representation, not that nice, but it is working just to see what happens. So you can now do all this stuff what elevator is normally doing. So going up and down, what happens if you have a power failure in the power system? What happens if you have a rope cut, for example? So what usually not happens. But just in case, we are prepared also for this, right? So if you're a big fan of Hollywood movies, there it happens sometimes, but not in the real world. So and now the user can just prepare and can just do his trip. There's also log file modus, so everything is logged in the background. So every interaction with the graphic user interface to replicate these simulations with different variants and configurations to see whether the behavior changed and so on. So for example, now there's an emergency stop because of a power failure. Via the plots, we can see the physical signals, position, speed, acceleration. Here, just as an example, just a bunch of this stuff. This can be exported, further analyzed inside MATLAB, inside Excel, whatever choice you have for the tool. And yeah, that's it for this. So just for a rough introduction to this. There's also something which is more automatized. So it's called load factors. It's a method used in our development. It's more or less the simulation of a factor. So there are different standardized test cases where you say, okay, so you load the elevator with this much load at this point in the shaft, and then you go this high and so on, and then you do this and this and this, and this is automatized in the whole thing. So the only thing you're really doing is clicking the start button, and then the simulations are done for all the different test cases, and the analysis is automatically done, and you just export your results, and then it's done. And this is all done outside MATLAB, just in your internet browser. Okay, the other thing, hardware in the loop. So, and now it comes really from physical testing to a model-based approach. Now maybe it becomes a bit confusing. I try my best to not create a big mess. So this is the system under test. It's our elevator controller. It is more the application layer of the elevator software. It is not this controlled software everyone knows for controlling motors and so on. It is more the application layer, really. So you have our real elevator controller, the EC, with the real PCBA, with the real software, the real process, CPU and so on. So then also the drive control, so the control of the machine is real. You have the real brake control, the sensoring system for the car position, for the car load is real, and also the safety circuit, so the safety device, so to say. And then it is looking like this on the left side, so it is roughly this big, weight, I don't know, 300 kilograms, something like this. It's our normal training simulator. This is already in place. And this is how the people were testing since years the stuff. The problem here is there's no elevator. So it's just a controller, but no elevator. This means you have no load, no friction effects, no bouncing effects of the ropes, simply no system behavior. And this leads, of course, to a big lack of things you could test with this stuff. So therefore, we created, or we optimized the model we already created to make it real-time, to run it in real time. So you have all the mechanical stuff I already told you. I marked it here in our model. So the gray parts are now real. The gray parts are model, the red part are real. So, and in the end, then we had a so-called tower in the box. You see it here in the corner. So in this little Speedgoat real-time box. So just if you imagine this controller stuff is really that big, and the whole mechanical shaft model is that big. So it's quite interesting. So it is a bit different like in the reality. And with this tower in the box, we are now able to perform every test like we are doing it in our real shaft. But before the mechanical stuff is ready, and also without occupying these test shafts, because this is costly and takes a lot of time, also the installation and so on. Here's a little example from the project. So the infrastructure we need for a so-called SRT, the software release test. So today we can just use one HIL test bench. Before we needed a complete test tower installation, 2 people testing and so on. And now we are focusing on a specific test. It's the so-called safety gear test. The safety gear is exactly what I mentioned. So if someone is cutting the ropes, whatever reason, the safety gear is the last instance of safety system and is mechanically breaking the cabin when it's falling down. And before it took up to 6 hours, sometimes 8 hours, depends a bit on how the tests were going. You have to load the car, you have to run a certain state machine, so to say, to bring the system into the right thing and the right position and to run these tests. And then also what is mostly more problematic is to release the stuff again. So put out the weights and put it into normal mode and so on. And this took up to 6-8 hours, something like this. Now we can do this within 90 seconds. So this without any issues, without any safety issues. We can also test what happens if the safety gear is not activating, for example. It's things we never could done before, because you can imagine if an elevator is just falling, it's just falling without braking. So you have a huge disaster. So even if you have a test environment, it's really dangerous for the people who are doing the tests. The test environment get crashed and so on. So this is, it's really not that good. So with this model-based approach, we can do this now. So this model-based approach, together with a test automation system, helps us also to increase the test coverage. Okay, so before, this is what I was talking about, because of the huge variance. If you just consider 3 dimensions, 3 parameters, like the shaft height, the weight of the car, and the nominal speed you want to run, so we were able to just cover these little spots for testing. But with the HIL approach, with the whole test automation, we can now cover a lot of more variance overnight to get a better maturity of the software and to have a better idea of what happens then. And this is also changing a bit the development paradigm from these worst case approaches to a real approach where you say, okay, so you can optimize your system for the different sweet spots. So conclusion, that's already it. As I mentioned, digital transformation is a change management project. So I asked the question to the presenter from Keyboards about how it is accepted. This is really a huge issue in our company. So because we are really mechanically focused, very old-fashioned, also the industry is very old-fashioned. The people are still believing or just believing physical test reports, so and nothing else. And there's really a journey to gain trust from them. And we did these now with best practice projects. So there are sometimes people which are a bit ahead of others, which have the trust in these things and which say, okay, let's make it happen. Let's try it out. So I have a project. Could you support us? And there it is really, really well accepted. So, but that's the only thing how it can go in our organization. Then, as I mentioned, the reduction of the time for the physical testing. So we had the software release test in one night now. Before it was 4 weeks, 2 people in the shaft. Yeah, and the other thing is the fact-based development. So as I mentioned, we have project. We already successfully supported people within several projects for different in different development stages, which what is also really interesting, because in the beginning we were just thinking on HIL late verification. This means in the process on a later stage. But we can also use all this desktop simulation with the web apps. We can use this for concept evaluations, for specification evaluations, for requirements checking in the beginning. And this is really a huge benefit. A little outlook. So what we want to do within the next steps. The project I showed you is for our newest controller generation, which is now located in Switzerland. We will deploy this to India, and also for the North American market, we will deploy such an HIL system to the US. And then the other point is the fully automated simulation process in the web apps, where really people can define their own cases. So yeah, run up and down, make here a break, make there a break, defining their configurations, putting an analysis and a reporting file into the system, and then just clicking the start button, leaving the PC, joining the next morning in the office and seeing the results. And this is what we are going for. Mainly, yeah. So I think I'm done with this. So thanks for your attention. Also, if it is quite near to the Apple, and yeah, thanks a lot again also to MathWorks to have this opportunity.